All right, so we're going to take a look at 2D motion in class problems, and we're on the back side. On the back, we've done I don't know if we did all the problems on the front, I'll be honest. We did 1, 2, and 3. I don't know if we did 4. I don't know if we did 4, but we're not going to do 4. We're going to take a look at in-class problem, 2D motion in-class problem number 5 and problem number 6 today. So, up till now, again, when we've gone through projectile motion, it's kind of by default been horizontal launch, but now we got to go through and say, is it horizontal or angled? And there's a worksheet called Angled Launch Projectile Motion Problems. Chances are really good that those are going to be angled launch, but the idea is we want to kind of go through, we want to ask ourselves this question. So if we take a look at in-class problem, 2D motion in-class problems, number 5. I'd strongly encourage you to draw pictures along the way. I think they're going to be helpful. I find them to be helpful. So problem number 5 on in-class problems, and again, if you can't find your 2D motion in-class problems, there's a stack just to the left of the phone, right on the top. They're there. So it's also linked on today's in-person agenda as a PD if you want to mark it up as PDF at home. Public service announcement right there. All right, so an arrow is shot at some angle, such that above the ground, such that the velocity in the x direction is 18 meters per second and is 23 meters per second in the y. Assume that the arrow lands at the same height in which it was fired. Assume that the arrow lands at the same height in which it was fired. Then, I'm going to say this one like 3 times. Let's make this assumption unless very specifically told otherwise. Unless very specifically told otherwise, we're going to assume that the object started and ended at the same height. So unless we very specifically tell you otherwise, it's a delta y is equal to 0 problem. Okay? Unless I very specifically tell you, like a car goes off a ramp and as it's going up, like landing at the bottom of a cliff, and then it lands at the bottom of a cliff. I throw a ball at some angle off of the building and it lands on the ground. Okay, that would be me specifically telling you otherwise. But if I don't, then we are going to be going with that. Okay, now there's 3 parts to this, an A, a B, and a C, and the intent is to kind of break it down. Okay, so I'm going to go through and I'd like to draw, I should draw a picture. I'm going to draw a picture first. So for in-class problem number 5, it's thrown at some angle, shot at some arrow, it's some arrow. And it has some VI. It doesn't tell us what that VI is, and we don't care with it. Even if I did know what that VI is, we don't use it. At some angle, and it doesn't tell me the angle, and the reason I don't tell you the angle, most of the time, sometimes I do, like on your homework sheet, I do, but it's really just for reference sake, to, hey, look, complementary angles do what? Okay, so at some angle. The key is angle launch, at some angle. Such that, oops, I should be pointing my camera over here. Such that the velocity in the x direction is 18 meters per second. So I'm telling you the VIX is equal to 18 meters per second. And 23 meters per second in the y. So VIY is equal to 23 meters per second. Now, what really is going on here? Trig functions is what's going on here. It's thrown at some angle, okay, with some speed. Then we do some sine, cosine, trig functions, which we don't do in conceptual physics, and we go through and say, hey, the cosine of VI times theta, the angle, is 18, and this is 23. But we don't do trig. So I'm giving you the VIX and the VY. I'm breaking this into its X and Y components is the term that we use. Okay, that's what's given in the problem. So as we work through our list of 2D of problem types on our 2D motion if-thens, we can go through and we can say, is it a 1D or 2D motion problem? It's 2D. So because it's 2D, I'm going to use my black marker, and I'm going to make two lists of variables, a delta x, a VIX, a VFX, an AX, and a T. And I'm going to make a delta y is equal to VIY, a VFY, and an AY, and a T, and the only thing that's in common is our time. This is the exact same thing we did with horizontal launch. Okay, black marker, 2D motion, two lists of variables linked by time. And let me talk briefly about that linked by time. When you guys were doing that progress quiz the other day, some people were going through and they're like, if only I knew one more number, I could then do this calculation. And they were working in the X column, and they're like, I just need another number. Hey, look, here's another number, and they steal, borrow, use, I guess it is. When you're doing a calculation in this column, you can only use numbers in this column in that equation. If you're solving for something in the Y, you can only use numbers in that column. People mix and match that X and Y stuff, and don't do it. Don't mix your X and Y stuff. 2D motion problem. Is it a projectile? Is the arrow moving freely through the air in 2 dimensions where the only force acting on it is gravity? Once it leaves the bow, an arrow is shot. So once it leaves the bow, in the absence of air resistance, is it moving freely through the air? And the answer is yes. So it's a projectile motion. So with my green marker, because it's a projectile motion problem, we can say my AX is equal to 0 meters per second squared. Because my AX is equal to 0, my VIX and my VFX are the same. Also, because it's a projectile motion problem, my AY is equal to negative G, which, because we're on Earth, unless very specifically told otherwise, is negative 9.8 meters per second squared. Projectile motion, green marker. Is it a horizontal launch? Is the arrow shot parallel to the ground, horizontal to the ground? No. Okay, it's at some angle, right? So because it's at some angle, it's an angled launch. Now I'm gonna write this down in 1 second, and then I'm gonna erase it, okay? According to my little chart, it says my VIY does not equal 0. I'm gonna erase this in one moment, because it's not super helpful. The idea is, if it was a horizontal launch, I would have put a 0 there. But it's not a horizontal launch, it's an angled launch. So because it's an angled launch problem, it's some number. We just don't happen to know what that number is. So because we don't know what that number is, I don't know why I was erasing it like that. It's some number. It's not 0. But just knowing that it's not 0 isn't something we can, like, it does not equal 0. You can't plug that in the equation. Okay, so it's not equal to 0. It's some value. It's not horizontal launch. That's really the emphasis there. Last part, is it a delta y is equal to 0 problem? Does that object start and end at the same height? And in this case, it says yes, let's assume that. And it says in the future, unless very specifically told otherwise, we will assume that as well. So because it's a delta y is equal to 0 problem, it starts here, it goes up, but it ends at the same height that it started. Because this is a delta y is equal to 0 problem, my VIY and my VFY are opposites of one another. Okay, and the way it's listed there, it says my VFY is equal to the opposite of my VIY. Now, depending on your algebra, you may do some substitutions with that, or if we give a number, it'll be kind of nice because we can just plug that in. Okay, so whatever my VIY is, which is actually given in this problem, is my VFY is going to be the opposite of that. That's for my problem types. Now let's look in the problem, and again, this is an arrow shot at some angle such that my horizontal velocity is 18 meters per second, and it's 23 meters per second in the y. So with my red marker, my Vx, my Vix is 18 meters per second. It's also my Vfx because it's a projectile with an acceleration of 0. And my VIY is equal to 23 meters per second, because that's what's given in the problem. Because my VIY is 23, my final velocity is equal to the opposite of my initial velocity, so my final velocity is equal to negative 23 meters per second. That's our list of stuff. Now we can start going through and answering the questions that are being asked. But there's a fair amount of information that we can gain, again, from problem types and problem types alone. So the first question is, how long is it in the air? That's just kind of a nice way to set you up for it. Hey, we should solve for time first, but realize if I don't ask you for time, it's a pretty common thing that we have to solve for time in the opposite column first. But I'm just asking you to solve for time. So we're trying to do, for part A, what we're asking is, let's solve for time. Now, if you take a look at your list, your X column and your Y column, which column do you think we're going to be better off trying to solve for time in? The X or the Y? And what I'm really asking is there one column that has enough variables to solve for t? Or do they both? Or does one have more? And y has more. You know, y has 4 out of the 5. Technically, they have 1, 2, 3 in the x, so we do have 3 numbers. We need to know 3 out of 4. The fact that these are the same kind of hurts us a little bit. So we don't really have enough information in the t. We're going to have to go in the y column. So when we go through and we solve for time, for part A, we're solving for time. So with part A, when we try to determine time, we have some choices. And we actually have 3 different equations we could use. We have 3 different equations. Because we know so many things, we know everything except for time, we could use equation number 2, we could use equation number 3, we could use equation number 5. And I'll show you what they are, and I'm going to erase the other ones. I'm going to do equation number 2. Okay, but I'll show you the other 2 that we could do as well. We could do equation number 3, and I'm going to erase this in a moment. But in the y direction, we do know delta y, VIYT plus 1/2 AYT squared. You know delta y, it's 0. You know VIY, it's 23. You know acceleration in the y direction is negative 9.8. So you could use equation number 3, and you could solve for time. However, you guys do have the math skills, but in order to solve for t, because it's t and t squared, conveniently that t and that one VIYT didn't cancel out because it's not equal to 0, you'd have to do quadratic or factor it, which in decimals you'd have to use quadratic. And I think this is correct. Negative b plus or minus the square root of b squared minus 4ac all over 2a, that right? Okay, you could. I'm not saying you need to, but you could. Okay, you could do equation number 3. You could do equation number 5. You could say delta y is equal to VFY plus VIY divided by 2 times t. And you could solve for t, because you know delta y is 0, you know this is negative 23, you know this is 23, you could then solve for t. That's fine, you could. You cannot use equation number 4, because equation number 4 doesn't have time in it. So that's not a choice. So I'm going to use equation number 2, but you could use 3, you could use 5. Equation number 2 was VFY is equal to VIY plus AY times t. I like equation number 2, nothing's squared, nothing's, it's not like an addition with a divided by. It's pretty, I don't know, I like it. It's relatively simple. There is, however, a pretty common math error people make in this next step. So I'll point it out. So we just plug in numbers. VFY is negative 23. VIY is positive 23. If you don't have that negative 23, you're going to get the wrong answer. AY is negative 9.8. So most people say, well, I got to get rid of this 23. Hey, Mrs. Davies. Okay, so the common mistake, people see this and say, well, I got to get rid of this. And they say positive 23 and a negative 23, those cancel each other out. And they don't. Okay, because in order to get this over here, we have to subtract 23, we have to subtract 23. So then this becomes negative 46 is equal to negative 9.8 times t. So negative 46 divided by negative 9.8 gives us a t of positive 4.6. 9387755 Okay, so that's our time. That's how long it takes to go from here to here. And that time is here. And that time is here. Okay, that's part A. Part B, how far? So for question B, now we're saying how far does this arrow travel? What is my delta x? So for part B, we're talking about the x direction. In the x direction, because this is equal to 0, equation number 3 is kind of the go-to. Number 3 says delta x is equal to VIX times t plus 1/2 AX times t squared. And because AX is 0, that's why equation number 3 is so nice in that x direction. And then what we're left with is delta x is equal to 18 times 4.6. And then we get a delta x of 84.48. For 897, so we round it up to 4.9 meters. So that's how far away my arrow lands. It lands 84.49 meters away. Now, as we get better with these problems, I don't ask you part A, and I just say, how far away does the arrow land? But then the idea is I can't do this step without finding my time first. That's kind of that's the progression. This is kind of like, I don't want to say it because I don't want to insult. It's kind of like baby stepping it. Not really, I'm not calling you guys babies. I don't mean that. Don't take offense to it. Sorry, everyone in there too. I don't mean offense to it. Okay, but it's kind of saying like, hey, we got to find time first. Then we can go through and do it. Part C. I don't love part C. I'm going to do part C kind of quick. And the reason for it is on the homework sheet, I do ask it a couple times. Part C is really a whole new problem. Part C is asking how high did the arrow go? And what that's really saying is if the arrow starts here, and it's going to end right there. Sorry, camera, you're not pointing at what I'm looking at. Okay, if it starts here and ends here, what I'm really saying is how high did it go? Which, if you kind of think about, well, isn't that really just max height problem? And if so, isn't that really just a 1D motion problem? And the answer is yes to both of those. Okay, so remember, the motion in the x direction is completely independent of the motion in the y direction. So no matter how fast this thing's moving in the x direction, we can look at the y direction as a 1D motion and a 1D motion problem alone. But because it's a max height problem, it's really a new list of variables, and I'm going to keep the y's in there just because that's kind of what we're used to right now. It's a 1D motion problem in the y direction, and that's it. But it's a new list of variables because in this problem we started way on the left and we ended way on the right. But now I only want to go from here to the maximum height. So what I'm asking is, what is our delta y? It's not 0 anymore. It doesn't start on the ground and end on the ground. I'm saying how high, what is the maximum height? It still was shot upwards such that the velocity in the y direction is 23 meters per second. It's still moving freely through the air, so therefore this is negative g, which is equal to negative 9.8 meters per second squared. And this t, we'll come back to this t. It's a max height problem. So because it's a max height problem, the velocity at maximum height is 0. That alone is enough information to solve for this. We could use equation number 4 because there's no time. However, we actually do know one more piece of information. In the previous part, we determined the total time in the air. And because it was a delta y is equal to 0 problem, the total time in the air is twice the time it took to get to max height. So, and that, I think it even, how is that worded? The time is 2 times larger than the time to max height. So because we calculated the time over here in part A, we technically do know this is 4.69 seconds divided by 2. We know the total time in the air because this is a delta y is equal to 0 problem, then half the time to max height. So roughly this is 2.345 seconds, just kind of dividing that. So if you want to use that time, you could. If you don't want to use that time, you don't have to. You could use equation number 4 that says VFY squared is equal to VIY squared plus 2AY times delta Y. We could do that. The other thing we could do is, because we know time, we could use equation number 3. We could use equation number 5. If we wanted to use that. And it's really kind of up to you at that point. But we could say, hey, this is 0, this is 23 squared plus 2 times negative 9.8 times delta y. And then if we go through and do the algebra on this, I don't even know. We're going to do this kind of all in the calculator. We get a max height of 26.99 meters. Is what I got. 23 squared divided by 19.6. Yeah. Okay. I want you to start number 6. So problem number 6 is an angle launch problem. Because it's an angle launch, it's a projectile motion problem. Because a projectile motion problem is a 2D motion problem. Okay, so I want you to give it problem number 6 a try. And okay, let me take a step back. I would like you to draw a picture for problem number 6, and I'd like you to make the list of variables for number 6. That's kind of where I want you to start. I'll give you a little bit of time. I want a picture, and I want this list filled in as best you can for problem number 6. And I will put problem number 6 on the screen. It says a ball is thrown at some angle such that the horizontal velocity, it has a horizontal velocity of 8 meters per second. If it lands 12 meters away, what was the initial vertical velocity? Okay, so draw a picture for number 6, make your list of variables, fill in all the information based upon problem types, and then the problem. I'll give you a minute or two. Recording, just so you know.
All right.
So we're supposed
I'll keep my potty mouth to a minimum.
to go. And it won't make it to the YouTube.
Looking at it.
Not good.
All right. Yeah, no problem.
Maybe wait, when those like 64 ounces, like.
Surge.
You guys know what surge is? Just out of record, with your own.
Sugar, that's all.
How about Jolt Cola?
Oh,
Jolt.
the bottle of sugar, that's all it is.
How about Red Bull? You guys know what Red Bull is? Monster.
Come on, everybody knows the Red Bull.
Well, just to know how old I am right now. So there was a soda that was called Surge. It was this green, like weird green color. I think it was kind of extra sugary and maybe a little extra caffeine. Jolt Cola, Jolt was the thing. It was like twice the caffeine and twice the sugar. How they advertised it. That seems necessary. So that was our jokes that we were making. All right, so let's talk about this one. So again, like I said, part A in the previous problem kind of got us to the, hey, you should solve for time first. And that's not gonna be that's kind of the next step is not. And that's what this problem is ultimately getting to. But this is what my picture, your picture should look similar to. I throw some ball at some angle, who cares what the angle is, we don't do trig anyways, such that, we should have a label here, my horizontal velocity is equal to 8 meters per second, and we don't know my DIY. That's what we're all asked to solve for. What was the initial vertical velocity? What was my DIY? It lands 12 meters away. Okay, so that's what my picture, that's the information I know from the problem. It's a 2D motion problem, so I make my list, my two lists that I use my black marker for. It was a projectile motion problem, so my AX is 0, so my VIX and my VFX are the same, and my AY is negative G, which is negative 9.8 meters per second squared. Green marker was because it was a projectile motion problem. Horizontal launch or angle launch, thrown at some angle, therefore it's an angled launch. This is not equal to 0 anymore. And because this is 0. And you can say, how do you know this is 0? Because in the previous problem, it said unless very specifically told otherwise, and this is, again, I said this like 3 times, unless very specifically stated otherwise, let's assume it's a delta y is equal to 0 problem. Because this is equal to 0, my final is going to be the opposite of my initial. It's not necessarily super helpful at this point in time. Some of you maybe would do like some type of algebra substitution that could be beneficial, but just realize that if we knew it, but that's kind of what we know. So then the question we're trying to solve for is my DIY. Are there questions about how did I get something? Oh, I'm sorry. Then this number came from the problem. It lands 12 meters away. It was horizontal velocity is 8 meters per second. That's why that was from the problem. Questions about where any of that information came from? Okay. So then the question is asking us to solve for this. I don't have enough information in this column, so therefore we're going to have to solve for t in the x column first. Now, in the x column, like our favorite equation is number 3. So equation number 3 in the x column would look something like this. In the x, equation number 3 is delta x is equal to VIX times t plus 1/2 AX times t squared. Because my AX is 0, that whole back term cancels out. 12 is equal to 8 times t. T, I'm pretty sure 12 divided by 8, you can check it, is 1.5. But 12 divided by 8, okay, good, 1.5. So because we now know this is 1.5, we also know that this is 1.5. Now in this column, I still don't know what this is. Don't know my final loss. So equation number 3 in the y direction is the one we want to use because we don't know my final loss. Could you do, I think you could technically use equation number 2. You could, I think, use equation number 2 because my final velocity is the opposite of my initial velocity. So you could substitute and say negative VIY is equal to VIY plus A times T. I'd stick with equation number 3 though. But you could, I'm pretty sure you could do that. Delta y is equal to VIY times T plus 1/2 AY times T squared. Because my delta y is 0, then we can say my VIY times 1.5 plus 1/2 negative 9.8 times 1.5 squared. So Excuse me. Okay, so that's what we get. Then we have to add 11.025 to both sides. So we end up with 11.025 is equal to VIY times 1.5. Divide both sides by 1.5. Divide by 1.5. And we get a VIY that's equal to 7.35 meters per second. Is what I got for an answer, and I hope I did it right. Okay, so these are these are angled launch problems where my delta y is equal to 0. If delta y is not equal to 0, it makes things more complicated. If delta y does not equal 0, then in order to determine time, you have two choices. And we'll go through these choices on Monday and Tuesday. But your choices are, if it's not a delta y is equal to 0 problem, to solve for time using quadratic. And so you might like, ooh, quadratic? Yes, quadratic. Or if you don't want to do quadratic, you can do an extra physics calculation where you could go through and you could solve for the other unknown first and then solve for time second. So you kind of have to say, do I want to do the quadratic equation, or do I want to determine what the other variable, do two physics calculations in order to calculate the time? And I'll kind of show you that come Monday or Tuesday. On the corner of my table right here is a worksheet called Angled Launch Projectile Motion Problems. This is a homework sheet. It is not due Monday. It is not due on Tuesday. I'm giving it to you now because it'd be good for you to work through. I think on the in-person agenda, I said the first 3 problems. The first one, the first 2 to 3, okay? If you go through and you come to school on Monday or Tuesday and you have the first 2 or 3 problems, you're gonna have a pretty good understanding of whether you can do angled launch with a delta y is equal to 0. If you don't, you might convince yourself that you do, and you really don't know how, okay? On the back, these last 2 are delta y not equal to 0, and that's what we're gonna address next week. I forgot to mention this at the beginning in class 2. I posted it in Canvas as a due date, as an assignment, that I think next week we will be wrapping up the unit, and then that Monday and Tuesday before Thanksgiving is gonna be the days we're gonna test. And some of you might know already, I'm not gonna be here the Monday and Tuesday before Thanksgiving. And if that's the case, then I would encourage you to take that test prior to Thanksgiving. If you say, I don't want to, or I'm not going to, or I'm not able to, we can figure it out. I'm just saying, if you aren't gonna be here the Monday, Tuesday before Thanksgiving, it's an entire week after that when we come back. And that, sometimes people think like, hey, I just get a little bit more time, then I'm gonna really understand this, and generally that's not the trend. Generally, if you say, hey, I'm just gonna wait like 7 days, but I'm not gonna do anything for those 7 days until the very end, things don't magically get better. So I would encourage you to get the help now. This homework sheet, I would encourage you to grab it now. Again, problems 1 and 2, 1, 2, and 3 is really what I would encourage and I'd like you to have done. There's nothing to submit at this point. It's just really to kind of get a start on it. The due date is set for next week when I want the whole sheet done. So it's on that corner though. If you have questions, please, please, please ask.